Okay, let's do one more example in this section. So on this one, what we've got is 5 kilograms of nitrogen undergoing a process from a pressure of 5 bar and a temperature of 400 Kelvin to a pressure of 2 bar and a temperature of 500 Kelvin. All right, so pressure's going down, temperature's going up. We're going to assume an ideal gas. That's important. And we want to find the change in entropy. Notice the units are kilojoules per kilojoules per Kelvin. So what variable are we looking for? We're looking for entropy or specific entropy? We're looking for capital S, right? So I want delta capital S. That's what we want. Now, the constant specific heats will be evaluated at 450, so we're going to do it that way. And then the second way will be if we have variable specific heats. All right, so two different ways of doing it. All right, and we'll use a different set of equations depending on the method. Okay, so first let's look at constant specific heat that's evaluated at a temperature of 450 Kelvin. All right. Now, we're going to have to look at our specific heats, so we're going to go to table A20 to do that. All right, and then here's that table. So here's A20. This is just the ideal gas for some of the common gases. So nitrogen is here. That's what we have. Our temperature is 450, right? So we're going to come over here to nitrogen. CP is 1.049. And notice the units, kilojoules per kilogram Kelvin. And then CV is going to be 0.752. All right, so we've got that number also. So let's write those down. All right, so CP was 1.049 kilojoules per kilogram Kelvin. CV is 0.752. It's kilojoules per kilogram Kelvin. All right, so now we've got those values. We are assuming that these are constant, right? Because we said we were looking at this temperature. That's what those values should be. They're going to stay the same. Now, when we have a constant specific heat, remember we had an equation we could use. So if we look back, this is what we had, right? So we wrote down if specific heats are constant, then you had these choices in equations. All right, so we need to figure out which one to use. So if you look at the information that we have, I've got temperature and pressure, all right, at both the states. So that means I want to use this second one. All right, because this one up here had specific volume. I'm not really told anything about specific volume. So we do know pressures though. So let's use this second equation here. So we have S1 minus S2, or S2 minus S1, I mean, equals CP times natural log of T2 over T1 minus R times natural log of P2 over P1. And remember this R, you're going to have to find it. So R is that R bar over the molecular weight for your substance, which ours is nitrogen. So if you look it up in table A1, your M value is 28.01. And the R value, or R bar, remember, is 8.314. And the units here will be kilojoules per kilogram Kelvin after they all cancel out. All right, and I didn't find this value, so we're just going to write that equation in over here. Okay, so S2 minus S1 is going to be CP, which is 1.049. Let's put our units here. And then times the natural log, and then we've got T2 over T1. T2 is 500. T1 is 400. All right, notice the units there cancel. And then we're going to have minus R, so let's write this down for R. And then times natural log of P2, which is 2 bar, over P1, which is 5 bar. The bars cancel there. So if you put this in your calculator, you're going to get S2 minus S1. It's going to equal 0.506. It's kilojoule per kilogram Kelvin. Okay, so this is specific entropy. That's your change in specific entropy. That's not what I wanted. I wanted the change in just regular entropy, the capital S, right? So to get that, then what we're going to do is get rid of this kilograms. And the way we do that is just by multiplying this number by the mass of the substance. So that's 5 kilograms. That was given in the problem right there. So we'll have 5 times 0.506. So that's 2.53 kilojoules per Kelvin. So that's going to be your change in entropy in your system if you have constant specific heats. Okay, so that's how you would do that. Now part B, we have variable specific heats. All right, so we can't just go to table A20 and then look up these two values and go from there. We got to do something different. All right, so we've got variable specific heats. So that means we're going to use a different equation. And let me find it. So that was going to be this one right here. Remember we said this was for if the C values were not constant. Right, so we're going to use this right here. So we get S2 minus S1 equals that standard entropy at T2 minus standard entropy at T1 minus R times natural log P2 over P1. Now these two things right here, those are going to come from the table, and that'll be table A23. So if we look at that table, here it is, and nitrogen is way over here. Okay, so what we're going to do is we're going to look at our temperature for the two states, and then we're going to come over here to this column. Now notice this column has a bar above it. All right, so that's telling you something's going on there. So if we look up here in the units, if we have the bar over it, it means the units will be kilojoules per kilomole Kelvin. Okay, I don't really want to use kilomoles, so we're going to have to figure out something with that. Okay, but let's go ahead, let's pull out our numbers that we need out of this table, and then we'll figure out what to do with that. Okay, so at T2, we've got a temperature of 500. So here's 500, we come down here, and we get 206.63. So that's that one. And then for T1, we've got 400. So that's 200.071. So let's write those values down. Okay, so to get this, we're going to look up in the table at 500 Kelvin. We got a value of 206.63. That was kilojoules per kilomole Kelvin. And then for this, the initial temperature was T1. We're going to get the entry of 200.071 kilojoules per kilomole Kelvin. Okay, now the way we're going to get rid of this kilomole is basically by dividing the molecular weight. So let's do that next. So S2 minus S1 is going to be the S bar term at T2 minus the S bar term at T1. And we're going to divide that by molecular weight, which is 28.01, right? That's what we had up here. Units for molecular weight are kilogram per kilomole. All right, and then we're going to subtract the R. All right, now R is not going to change, right? It's still up here, this right here. So 8.314 over 28.01. And then we want the natural log of P2 over P1. P2 is 2 bar, P1 is 5 bar. All right, and then what we're left with is just basically plugging in these numbers here. So let's do that next. So this first one at T2 was 206.63. Then we subtract 200.071. We're going to divide by 2801. Now that's going to cancel out the kilomole, which is what we wanted to do. So now the kilomole cancels. Now we end up with kilojoules per kilogram Kelvin for this term here. Then we subtract this term, all right? And when we do this term in the calculator, when we do the natural log, we're going to get a negative. So we're going to have minus negative 0.272 units here, kilojoules per kilogram Kelvin. So then S2 minus S1 is going to be 0.0, actually not 0.0. It's going to be 0.5062 kilojoules per kilogram Kelvin. All right, so this is our change in specific entropy. All right, so I want the change in regular entropy. So what do? We'll multiply by the mass, right? That gets rid of the kilograms. So we've got 5 kilograms, and then we're going to multiply by 0.5062, and then that gives us 2.531 kilojoules per Kelvin. And there you have it. All right, so just about what we had before. But that's how you know when to use this right here. When it tells you you have a variable specific heat, you can use that expression right there to get your results. All right, so hopefully that made sense. So in the next video, we're going to keep going. We're going to talk about closed systems a little bit more, and then after that we will go into control volumes. All right, so I'll see y'all next time.